Welcome back, guys. Today we're going to look at the distance formula and the midpoint formula, and we're also going to talk about circles. Before we look at the formulas for distance and midpoint, let's just do a quick review of the Cartesian coordinate system. We have a horizontal axis and a vertical axis. The horizontal axis is our x-axis, the vertical is our y-axis, and this breaks our coordinate system into 4 quadrants. Our first quadrant, second quadrant, third quadrant, and fourth quadrant. And all ordered pairs are written x coordinate, comma, y coordinate. Now, when we're talking about distance formulas and midpoint formulas, specifically distance, we're going to be looking at the distance between 2 points on the coordinate system. So be careful, we're not talking about the distance formula with regards to rate and time. So there are 2 distance formulas that you'll learn about, but this one is just the distance between 2 ordered pairs, x1, y1, x2, y2. So the formula for distance is d equals the square root x2 minus x1 squared plus y2 minus y1 squared. And all of that is underneath the square root bar. Now, this is a pretty beefy formula. We're going to learn another technique for finding distance in a minute, but first let's just practice using this. Find the distance between the 2 points, 3, -4, and 5, 4. We're going to call 3, 4, or 3, -4, x1, y1, and 5, 4, x2, y2. And before I start plugging into the formula, a really great exercise to help you memorize these formulas is to continue to write them down. A lot of times students have the formula in their notes and they're just looking back and forth when they plug in. But if you constantly rewrite that entire formula before you start plugging into it, eventually your muscle memory is going to help you retain that formula. So we're going to do that now. Distance is equal to the square root x2 minus x1 squared plus y2 minus y1 squared, all under the square root. And now that I've written it down, we'll start substituting our values in. So we have the square root. X2 is 5 minus 3 squared plus 4 minus -4 squared. Simplifying inside the parentheses, 5 minus 3 is 2 squared plus 4 minus -4 is the same as 4 plus 4, or 8 squared. 2 squared is 4, 8 squared is 64. We have the square root of 68. Now, when we are dealing with radicals, you always want to make sure that you simplify your answer completely. Same with fractions. But with a radical, when we're simplifying this, we're looking for factors that are perfect squares. So 68 has 2 factors, 4 times 17. Where 4 is a perfect square. So when I'm simplifying this radical, I can pull out the square root of 4, which is 2, and I'm left with the square root of 17, which is our final answer for our distance. Now, as I mentioned previously, there's another technique for finding distance, which doesn't require using that beefy distance formula. Most of us don't have too much of an issue remembering or recalling the Pythagorean Theorem. The Pythagorean Theorem is a squared plus b squared equals c squared. Now, the thing we want to make sure we remember is that the Pythagorean Theorem is used to relate the sides of a right triangle. A and B are the legs of your triangle. It doesn't matter which one you call A, which one you call B, but what is important is that you call that diagonal, the longest side, also called the hypotenuse, that's C. So let's look at a similar exercise and see how we can use the Pythagorean theorem to find distance. So we've got 4, -3, and 6, 4. The first thing that we're going to do is we're going to plot these 2 points. So 4, -3, that's going to be in our 4th quadrant, down here. And 6, 4, that's our 1st quadrant, 6, 4. And what we want to do is construct a right triangle using those two. So we're going to drop a vertical segment, make a horizontal segment, and eventually connecting those 2 points with the diagonal or the hypotenuse of our right triangle. Now, using this triangle, we can identify the lengths of the legs. We can count horizontal units and vertical units. We can't count these diagonal units. So this length is 2. This length is 1, 2, 3, 4, 5, 6, 7. Now, using the Pythagorean Theorem, we have 2 squared plus 7 squared equals this diagonal, which is C, which is actually representing our distance D squared. 2 squared is 4, plus 7 squared is 49. 4 plus 49 is 53. And when we take the square root, we get that the distance between those 2 points is the square root of 53. Now, 53 is going to be prime, so we're not going to be able to simplify that any further. And one more note about this, as we've seen in previous examples, and maybe this is something that you remember from another class, if you're taking the square root of both sides to solve for a variable, typically we have to add plus or minus. However, in this application, since we're dealing with distance, when I take the square root, I'm only giving the principal root, which is that positive square root, okay? Because distance cannot be negative. So here's just again to recap, this is just another way of finding distance that doesn't require memorizing the distance formula. Verify that the triangle formed by the points is a right triangle. So we've got 3 points, -2, 5, 1, 3, and -1, 0. And these are going to be the vertices of my triangle. Now, before we start investigating the triangle formed by these points, we first have to remember and recall the characteristics of a right triangle, because that's what's going to help us identify whether or not the triangle we draw is right. So how do we know if a triangle, any triangle, is a right triangle? Well, it has to have a right angle. Now, if I think about a right angle is 90 degrees. And if I think about 2 segments that form 90 degrees, we say that those 2 segments are perpendicular. And hopefully we recall from any examples or exercises where you are trying to write the equation of a line, perpendicular segments have slopes that are opposite reciprocals. For example, 2/3 and -3/2, those would be opposite reciprocals. Another way to prove that a triangle is a right triangle is to verify that the side lengths satisfy the Pythagorean theorem. So continuing with this example, let's prove whether or not this is a right triangle. I'm going to start by plotting these points. That's going to give me something to start with. I want to at least look at the picture and see if it even is possible that it's a right triangle, because you might find that you get 3 points and you can clearly see it's scaling. It's not a right triangle. So we're going to investigate first just looking at the picture. -2, 5. 1, 3, and -1, 0. All right, so looking at this, this triangle, do we think that it could be a right triangle? Now, in order to answer this question, make sure you think about tilting your head, changing the orientation of that triangle, because it's not a requirement that a right triangle lays nicely on one of its legs. So if you tilt your head a little bit this way, can you see that perhaps we might have a right angle here? Now, we don't know that for sure, but it at least looks like it could be a right angle. So I have reason to justify proving whether or not this is a right triangle. If I wasn't convinced that this could be a right angle, then maybe I would just say, nope, it's not a right triangle, without going through the necessary steps to prove that conclusion. Now, thinking about the two techniques that we have to prove a right triangle. The first one we talked about dealt with determining whether or not we had a right angle. Now, we think that this is our right angle based on the diagram that we've shown. So if we can prove that this segment, if you guys are following my cursor on the graph, if we can prove that this segment is perpendicular to this segment, then that would be enough to justify that this is a right triangle. Now, the second option requires that we use the Pythagorean theorem. Now, that's going to be quite longer of a process, because we're going to have to find the lengths of all three of these sides. Since the orientation of my triangle is such that it's resting on one of its vertices, I can't just count any of the lengths. So like we saw in that previous example where I was able to just count the sides and plug that into the Pythagorean theorem, I'm not going to have that option here. I'm going to have to use the distance formula to find the lengths of all three sides. Then I'm going to have to take those lengths, plug them into the Pythagorean theorem, and make sure that it satisfies the Pythagorean theorem. Since that's going to be quite time consuming, we're going to use the alternate method of proving that two line segments are perpendicular. And this is always going to typically, well, not always, but typically going to be much faster. So I'm going to label these points. This was point A, this was B, and this was C. And that's just going to help me label my work. I'm going to find the slope of segment AB. Now, you can either use the slope formula because we have those points, or you can actually just count the units going down 2 to the right 3, which gives us a slope of negative 2/3. But let's review the slope formula. It's y2 minus y1 over x2 minus x1. 3 minus 5 is negative 2. 1 minus negative 2 is 1 plus 2, or 3. Now, according to our diagram, it appears as though that's perpendicular to segment BC, so we're going to look at that next. Excuse me. So again, using my ordered pairs in the slope formula, y2 minus y1 over x2 minus x1. Negative 3 over negative 2, which simplifies to 3 over 2. And now we can see that these are, in fact, opposite reciprocals. So we can conclude that AB is perpendicular to BC. And therefore, that's what that symbol represents. Therefore, triangle ABC is a right triangle. Now let's talk about midpoint formula. When I think about midpoint and I think about I've got 2 points on my graph, the midpoint is halfway through it. Now, another idea of halfway through something or halfway between two things is the average. And that's exactly how we find the midpoint of 2 points. We're averaging our x values and we're averaging our y values. Now, if I know how to find the average, it requires me to memorize one less formula. To find the average of two values, you add them up and divide by 2. So the average of my x's would be x1 plus x2 over 2. The average of my y's would be y1 plus y2 over 2. And that is the midpoint formula. Now, if you keep on thinking about midpoint formula as average, it will make it a little bit easier because you'll see that there are similar expressions like the x1 and the x2. In the distance formula, it was x2 minus x1. In this one, it's x1 plus x2. So to keep that straight, where you use a plus sign, where you use a minus sign, if you just understand the formulas a little bit better, it won't be like just straight memorization. Find the midpoint between the points 2, -3 and 4, 2. So we're averaging our x's, 2 plus 4 over 2. We're averaging our y's, -3 plus 2 over 2. And now we just simplify. 2 plus 4 is 6. -3 plus 2 is -1. And that first x coordinate we can simplify further. 6 over 2 is 3. And my y coordinate is -1/2. Now, a way you can double check this is to quickly sketch these points. 2, -3 is in the fourth quadrant, so I'm going to quickly sketch that point right here. 4, 2 is in the first quadrant. So looking at this diagram, I can see that my midpoint needs to be somewhere between that. So maybe around here, if you can see my cursor moving. Well, what was the point that I just found was 3, -1/2. If I plot that, it looks directly in the middle of those 2 points, so I think I'm good to go. So this is just a really quick way to check to make sure that you didn't maybe miss a sign or something and that your point is accurate. A Little League baseball field is a square, 60 feet on each side. Find the distance from home plate to second base. So for those of you who are unfamiliar with a baseball diamond, we have home plate, first base, second base, third base. Now this makes a square. So here's home plate, here's first base, second base, third base. Now, the problem is telling us that each of these sides are 60 feet. They want us to find the distance from home plate to second base. So we're looking for this length right here. Since this is a square, this is a right angle, which means we can use the Pythagorean Theorem to find that distance. 60 squared plus 60 squared equals our hypotenuse squared. $60 squared is 3,600. So we get x squared equals 7,200. And then we're just going to simplify this after we take the square root. This is 3,600 times 2, which I knew just from that previous step. And 3,600 is a perfect square. It is 60. So the distance between home plate and second base is 60 square root of 2 feet. Next, we're going to shift gear and talk about circles. Circles is a unique topic. It's one of the first conics that we learn about. And if you ever take a course in pre-calculus, you'll learn more about circles. But just to introduce them briefly, the standard form of a circle is x minus h squared plus y minus k squared equals r squared. And two of the most important components of a circle are the center, which when the function is in, or sorry, not the function, when the circle is in standard form, the center is at the point hk. And the other important component is the radius, which comes from r. Write the equation of a circle in standard form with a center at -3, 5 and the radius of 3. Just like I did with the distance formula, when you're trying to memorize these formulas, if you continue to write them out rather than just substituting into them, you'll find that you have an easier time remembering them. So my standard form, x minus h squared plus y minus k squared equals r squared. Now looking at this ordered pair for my center, -3 is my h and 5 is my k. 3 is my r. So now when we substitute in, we have x minus -3 squared plus y minus 5 squared equals 3 squared. Now notice what happens. My standard form is x minus h, but because my x coordinate was negative, this is actually going to simplify to x plus 3 squared plus y minus 5 squared equals 9. So what we observe, and this is something that we're going to be doing in another example, the center is actually going to give the opposite sign. So when I had a negative x coordinate, my term became x plus 3. When I had a positive y coordinate, my term remained y minus 5, or my expression. So let's see that in this example where we're going to start graphing. X minus 3 squared plus y plus 1 squared equals 4. In order to graph, the first thing we need to identify is the center. This is my x minus h. The x and the x line up, the minus and the minus line up, which means h is equal to 3. Now, if I look at the second binomial, y minus k is expressed by y plus 1. The y's line up, but now instead of a minus sign, I've got a plus sign. So how do I get a plus sign in there? Well, what I had to do was subtract a negative. If I take y and subtract -1, that becomes y plus 1. So that is what identifies my value of k as -1. Now, generally speaking, you're just going to take the opposite sign. So if it's -3, your x coordinate is going to be +3. If it's +1, your y coordinate is going to be -1. And then we also need our radius. Our radius is the square root of this constant, the square root of 4, which is 2. So to graph this, I'm going to start by plotting my center, 3, -1. And I'm going to plot 4 additional points. I'm going to plot 1 point up, 1 point to the left, 1 point down, and 1 point to the right of that center, going that number of units that is our radius. So I'm going to go 2 up, 2 left, 2 down, 2 to the right, and those 4 points are going to help me shape my circle. Now we're freehanding it, so it's not going to be perfect, but try to do the best you can. Now looking at this graph, let's identify the domain and the range. Okay, I'm going to do domain in red. The domain are the values of x for which the equation is defined. So my graph, if I'm looking at my x-axis, my graph is bounded between these 2 points on my x-axis, which gives me my domain. My domain goes from 1 to 5. I'm going to do the range in this light blue. Hopefully we can see that pretty well. We're getting cut off a little bit. Okay, the range is going to be in this light blue. And the same thing, I'm looking at my y-axis and I'm trying to bound my graph between some values on the y-axis. Okay, I'm going to extend these horizontal lines so that I know I'm including the entire circle. But we can see that this entire circle is bounded between these lines on the y-axis, which helps us set up the shaded region for our range. The interval for that is from -3 to +1. So just to review, we were looking at distance formulas and midpoint formulas. Distance formula is a little bit tricky to remember. There's a lot of different elements. We got to make sure that we memorize it correctly. But we also saw that we can use the Pythagorean Theorem as an alternate method to finding distance. With midpoint formula, the thing to remember is that we are just finding the average of our x's and the average of our y's. We're pretty good at that concept of average at this point in our lives. So that should be a much better way of trying to remember that formula so that we don't mix up the signs. Then we looked at circles. We're only dealing with standard form of a circle at this point. When you guys move up into higher level math courses, you'll start looking at general form and things like that. But for right now, we're just hitting the surface with standard form, identifying the center and the radius from standard form, and then using that information to graph that circle. Hope you guys have a great day, and we'll see you next time.